This is part 1 of Unit 1, Lesson 6, Limits and Continuity. This lesson is going to take our understanding of limits and limit notation and define continuity at a point. Now, this is important that you guys grasp this, as this is something that comes out throughout the course. So understanding continuity is a very big section of this course. So the first topic we're going to be looking at is actually defining continuity at a point. So in example 1, we are to use the graph below to complete the table. Should look for 3 conditions that are necessary to satisfy the definition of continuity. That is, what 3 conditions must exist in order for f of x to be continuous at a point x equals c. So we're not looking at the function as a whole being continuous, just at a point. So those 3 conditions are that f of c is defined, has to be a value at c for the function. The second is the limit as x approaches c of the function equals some real value L, and that exists. And finally, the value of the function has to equal the value of the limit at c. So those 3 conditions must be met in order for this function to be continuous at a point. So let's go through and fill in the table. That'll help solidify the definition a little bit. So what we're looking at, values of x, and then we have to find if the function value exists. We should find the left-hand limit, the right-hand limit, and if those are the same, we can find the general limit, and then we can make a determination whether or not it's continuous. So I am going to split my screen here. Let's see if I can do this. So we can have the table here, and then the graph there. Okay, let me make this a little smaller. Oops. There we go. Got everything we need here. All right. So for the first value, x equals 9. So let's see if the value of the function exists at 9. And when we look at x equals 9, we have a dark dot here. So I'm going to call that 3.5. I know the dot's a little higher, but just for simplicity, 3.5. Then we have to find the limit from the left. So if we trace this curve here from the left, we're going to see that we get the same value here. From the right, but the function ends here on the right, so that's not going to work. So this does not exist. So the limit does not exist because the left and right hand limits aren't well defined in the same. So it is a continuous, and the answer to that is no, because it doesn't meet our 3 conditions. So let's look at x equals 4. At x equals 4, the value of the function does not exist. The left-hand limit does not exist because the function on the left ends. It doesn't continue here between 3 and 4, so that does not exist. The right-hand limit is now going this way, and that is an infinite limit, and there is no general limit, so it is not continuous. We could have said that after the fact that the value at 4 wasn't a real value or exists at all, but I just wanted to go through that. Okay, the next number is at x equals 3. So at 3, we have this dot right here. So, and that's at 9. And then from the left, we're tracing this along the left-hand side, we get 9. From the right, we have nothing here. on this side, so that does not exist. We don't have one continuous point yet. So the general limit does not exist. So the function is not continuous at 3. Okay, at 0, let me erase this a little bit. At 0, let me use my blue pen. That's weirding me out, going blue, red like that. So at x equals 0, so if we go to x equals 0, we have this point that's at 6. The limit from the left is 6. The limit from the right is 6. So the general limit is 6. And since the limit and the value equal each other, we finally have a yes. So then at -3, so we're here at -3, the value of the function is -6. The limit from the left is 5. Is that 5 or 4? 5. Let me erase that. I got too much stuff going on here. Okay, at 3, the limit is 5. And from the right, it is also 5. So the limit exists, that's 5. But they don't equal each other. We have a -6 for a value and a limit of 5. So this is a no. And then finally at -5, we have the value of the function is -2. From the left, the limit is -2. That's promising. From the right, though, we're up here and we get 7. So the limit does not exist. So it cannot be continuous. So that's the first example. All right, so while limits told us where a function intended to go, continuity guarantees that the function actually made it there. That's a really, really nice statement to remember. Limits tell us where we're intended to go, but continuity guarantees that the function actually got there. Because remember, we always say the limit as x approaches a number, but continuity at a point says we actually got to that number. Okay, so classifying discontinuities, and these should be kind of a review for you. Let me move this up a bit. So removable or point holes. Okay, the limit exists. So what we can, looking at this one, what we can say is the limit exists at 1, but it's not continuous. Because the value of the function isn't there. We could say that f of 1 does not exist. So it can't be continuous. You have jump, and the reason why this does not exist is besides the function, the limit does not exist. The next one is if at least one of the one-sided limits doesn't exist. And in this case, which both don't, we want to remember the limit must be a real number. It can't be infinite. Okay, here, this is another version of a hole. We don't have that hard cusp there like we did in the first one. It's a smooth curve, but we do have a hole there. There's a different type of jump where we do have a value of a function, but the left and right hand limits aren't the same, so the limit doesn't exist. And in this picture, the last one, we have one side that has an infinite limit, but the other side is well-defined limit. So they're all examples of discontinuities. So let's go to example 2. I don't know why I did that. Example 2. Find the points or intervals at which the function is continuous and the points at which the function is discontinuous on the interval, -5 to 10. So what we want to look are where we're well-defined left and right hand limits. Okay? So what we're going to see is that, I'm trying to read my notes, I'm sorry, is that it is going to be continuous from, why am I like this? Okay. It is going to be continuous. It's continuous from -5 to here. It's going to stop. Let me use the highlighter. It's going to stop right here at being continuous because we have a hole and the value of the function is up here. So -5 to -3. And then after that, it's continuous even over this change of function here because the limits meet and the points here. And it's continuous up to, but not including, +3. And then after that, from 3, and it's not continuous at 5 because there's a hole there again. And then it's continuous from 5 to, and again there's a jump at 7. And then after that, we can't say that it's continuous anymore. I guess we can. Yep, from 7 to 10. Because we're just going to 10. I forgot the interval stops at 10. Okay, and where are the discontinuities at? Everywhere that we had to stop or start an interval. So the discontinuities are at x equals -3. We had a hole. At x equals 3, we had a vertical asymptote. At x equals 5, we had another hole. And at x equals 7, we had a jump. Okay, so that's that problem. Okay, next. Okay, continuity. So some facts and theorems. So you can have one-sided continuity. A function f of x is called left continuous at x equals c if from the limit from the left here and the value of the function are the same. And right continuity at a point is if the limit from the right at that point and the value of the function are the same. And we had that a couple times in our previous examples. So if we look at just the this example 2 here, we had that at x equals 7. You can see that here because we had left-hand continuity because the limit from the left and the value of the function were the same. So we had left-hand continuity. And at x equals -1, we could say we had left-hand and right-handed continuity because it's continuous. So anything that is continuous, you can say that it's also one-sided continuous as well. Okay. Then we also have continuity at a point. Suppose f of x is defined on an open interval containing x equals c. Then f is continuous at x equals c if the limit as f of x approaches c equals f of c, which is what we said on the first page when we were doing that investigation. That's our 3 points. We know the limit exists. And so the left and right hand limits are equal. And the value of the function is equal to the value of the limit. Okay, that's the formal definition of continuity. So then we have two different types of continuity. We can have continuity on an open interval, is where we are not we're not including the endpoints, but it's continuous at every point in between them. So that's what we defined in example 2, that we had open intervals. So the function was continuous on those open intervals, but the endpoints, it was not continuous. And so the opposite is true for continuity on a closed interval, not only is it continuous at the endpoints, it's also continuous at every point in the open interval. So, and the thing to be careful of with this one is this part. And the function is continuous from the right at A and from the left at B. So it doesn't have to be both sides at the endpoint. It can be one side continuous. It has to be the correct one. So if A, you have an interval, here's A, and here's B. And let's say this part of the function, oh, I was afraid of that. This part of the function past A does not exist. Like, let's say that's all we have. So that part is telling us that if we come at A from the right, that has to be continuous, but we don't have to look at the left side because that's the end of the interval. We don't care what happens outside the interval. And the same with B. If we're coming at B from the left, we don't have to look beyond B. We don't have to look from the right because that's the end of the interval. Okay, so now we're going to look at some continuity laws of some basic functions. So as you guys probably already know, because I know I talked about this a lot in pre-calculus, polynomial functions are continuous over the entire reals. Rational functions are continuous on its domain such that Q of C is not equal to 0. So in other words, the 0 is at the denominator. Y equals x of 1 over n is continuous on all reals if n is odd, and continuous on 0 to infinity, excuse me, if n is even. These are our power functions. If you remember the graphs of our power functions, for them to be continuous for an even power, it was only from 0 to infinity, but they were continuous if n was odd everywhere. So we know from sine and cosine are continuous. B to the x, we know exponential functions are continuous for b greater than 0 and b can't be 1. Log functions are continuous as long as x is greater than 0, b is greater than 0, and b cannot equal 1. And then for inverse functions, if f of x is continuous on an interval with a range r, and the inverse exists, then the inverse is continuous. So you have two things there. F is continuous on the range, because that's going to end up being the domain of your inverse function. The inverse exists, and therefore the inverse is continuous on the domain, which would be that range. Some basic properties of continuity. Let's take a look at those. If f and g are continuous at x equals c, then the following functions are also continuous at c. If you multiply by a scalar, which is just a number, if you add or subtract them, if you multiply the two functions, if you take the quotient, and you want to remember that there is the possibility that at x equals c, g could equal 0, so you want to make sure that that doesn't occur. And then finally, doing the composition of those functions, if g is continuous at c and f is continuous at g of c, because that's the other condition. So if you're doing f of g of x, which shows here, g has to be continuous at that point, but you have to make sure that f is continuous at the y of that point for the composition to be continuous. So what I'm going to do is I'm going to stop here for part 1, and we're going to use these properties in some examples in part 2.